Okay, so before we start today, an announcement that we will have a quiz on Monday. Okay. Today we won't quite finish chapter 10. We'll discuss three more addition reactions: hydration, halogenation, and halohydrin formation. So we'll cover hydroboration oxidation on Monday before we start chapter 11. So that won't be part of the quiz, but these reactions and anything we've already covered could be on the quiz that we'll have on Monday. Okay. All right. So this slide here shows us a summary of the hydrohalogenation reaction that we learned on Wednesday. Discussion of the mechanism, the regiochemistry, which is explained by Markovnikov's rule. The more substituted alkyl halide is formed. And then the stereochemistry, both syn and anti-addition, a consequence of the fact that a carbocation is formed in this reaction. Okay, so you should be able to explain all of these points based on your understanding of the reaction mechanism. So our next reaction that we're learning is the hydration reaction. Okay, and I forgot to erase this arrow. I'll put that in later. But we're discussing the forward reaction currently. So if you take an alkene and you react it with one of our strong acids where the conjugate base is not a nucleophile, such as H2SO4, and you do that in the presence of water, you perform a hydration, which means you add the elements of water across your double bond, protonating one of the carbons and adding an OH group to the other one. Okay? So this is referred to as hydration. Since the mechanism is very similar to the mechanism of hydrohalogenation, we're just going to look at it on the screen instead of drawing it on the board, and we'll discuss how it differs. So the first step is the same. We're going to protonate our alkene. Our nucleophilic alkene attacks our electrophilic acid, and that forms our carbocation. You'll notice that instead of showing sulfuric acid, the book is showing H3O+. Of course, if you dissolve sulfuric acid in water, you generate H3O+. So that's why we're using that in the mechanism. You could draw it with sulfuric acid. It wouldn't really matter. Okay? So the first step is the same as the first step in the hydrohalogenation reaction. But the second step is different because our conjugate base, our HSO4- is not a nucleophile. We use water as our nucleophile, and that will attack our carbocation, generating an oxonium ion. Since water is a neutral nucleophile, we now have to have a third step. We have to deprotonate the oxonium ion that forms to give the alcohol product. You'll notice that what happens when we do that is we regenerate our acid. So this reaction is catalytic in acid, as the book notes here. And so you don't have to use a 1-to-1 ratio of your acid to your alkene. Question? Because the HSO4- is highly resonance stabilized. That's one reason. And then the other reason is simply concentration related. You have a lot more water molecules in the reaction mixture than you have HSO4-. Okay? Does that answer your question, or do you have another one? It is less basic than H. So if you look at the pKa's, sulfuric acid is a stronger acid than H3O+. So, right. And you can see that because if you dissolve sulfuric acid in water, you get H3O+. So that's a sign that H3O+ would have to be a weaker acid than sulfuric acid. Okay, good questions. So a couple consequences of this mechanism. Because the addition is the same essentially as the hydrohalogenation addition in terms of mechanism, the reaction will follow Markovnikov's rule. We're going to protonate the less substituted carbon of the alkene to generate the more substituted carbocation. So what that means is we'll form the more substituted alcohol. And you can see that the example I've drawn here on the board, we formed the more substituted alcohol. Okay. So Markovnikov's rule, just like with the hydration reaction. Okay, next consequence is that we have both syn and anti-addition. We had that with the hydrohalogenation reaction, syn and anti-addition. And so we see the same thing in the hydration reaction. Okay. And then because we have a carbocation intermediate, what do we need to be on the lookout for? Rearrangements. Rearrangements can occur in hydration reactions in the same way that they can occur in hydrohalogenations. So if you remember way back to chapter 9, we learned that if you treat an alcohol with sulfuric acid, you perform a dehydration reaction and you obtain an alkene as the product. So this reaction is in fact reversible. We can react alkenes with sulfuric acid in the presence of water to obtain alcohols. And we can react alcohols with sulfuric acid and obtain alkenes in water. This is a reversible process. In which direction does the equilibrium lie? To the left or the right? Okay, I've seen hands going in both directions. What did we learn about? Some people are pointing left, some people are pointing right. Okay, left, right is actually the correct answer. Remember, addition reactions, we're exchanging a pi bond for a sigma bond. Okay, so they're exothermic. We're forming more stable bonds than we're breaking when we're doing the addition reaction. We're going uphill when we make the pi bond. In chapter 9, we said we could drive the reaction in the endothermic direction. How did we do that? We talked about using Le Chatelier's principle. Yeah, removing one of the products. In this particular case, this alkene would have a much lower boiling point than the alcohol or the water. So you would run the reaction at a temperature where you could distill this off and remove it from the reaction mixture as it's being formed. And by Le Chatelier's principle, you'd form more of it. Okay. We don't need to drive it in the right direction, but when we are performing a hydration, we typically use a large excess of water. And so that's another way of ensuring that we consume all of our alkene to generate a quantitative yield of our alcohol. Okay. Any questions? Yes, Claire. Okay, so there is a difference in the bond dissociation energy of the carbon-hydrogen sigma bonds, if that's what you're getting at. But that's not quite enough to compensate for the fact that we are trading a sigma bond. We're breaking a sigma bond here, a carbon-oxygen sigma bond here, and replacing it with a carbon-carbon pi bond. So it's going to be endothermic in this direction, but we can manipulate that because Le Chatelier's principle allows us to manipulate equilibria. Okay. So reversible equilibrium process, we can push the reaction in either direction. And then there's another principle of reversible reactions or equilibria that we need to learn. This is not in the book, but it's important. The principle of microscopic reversibility. And what the principle of microscopic reversibility tells us is that in an equilibrium process, the same transition states and intermediates are encountered in either direction. Okay? So the principle of microscopic reversibility reminds me of mountain biking, one of my favorite hobbies. Is there anybody in the class who's ever been and mountain biked on the Slick Rock Trail in Moab? Good. I was hoping that Morgan would have done that before. I know you're a mountain biker. So the Slick Rock Trail, the major portion of it is a loop. Have you ridden it in the clockwise direction, counterclockwise, or both? Okay, only in one direction. But could you ride it in the other direction? You would. Would you encounter the same peaks and valleys? You would. You just encounter them in an opposite direction. I've ridden it in both directions. It's fun either way. Clockwise is a little bit better if you're going to go do it sometime, in my opinion. But the Slick Rock Bike Trail illustrates this principle perfectly because it has a ton of peaks and a ton of valleys. And no matter which direction you ride it, you encounter the same peaks and valleys. You just encounter them in the opposite order. That's what happens in an equilibrium reaction or a reversible reaction. Your transition states are the peaks. The intermediates are the valleys. And they're going to be the same. You will just encounter them in the opposite order depending on which way you're going in the reaction. So let's take a look at this. Let's pretend we're going to perform a dehydration. We would be starting with the alcohol. And if we were going to perform a dehydration, we would protonate the oxygen and we'd form an oxonium ion. So that would be our first intermediate. Then if we were dehydrating, we would lose water to get a carbocation. There's our second intermediate. Okay? And then once we get to the carbocation, we would deprotonate it with water to give or with the conjugate base of our acid to give our alkene. So you see, we would have the same intermediates, and then we would have the same transition states in between those intermediates, whether we were going in the forward direction, as shown on this slide, doing a hydration reaction, or the reverse direction, performing a dehydration. The advantage of that comes when we're trying to learn mechanisms, which means that once we learn the mechanism in the forward direction, we already know the mechanism in the reverse direction. We already know which intermediates we're going to be forming. We just have to reverse the order that we would encounter those intermediates. So it makes it easier. This principle makes it easier for us to learn mechanisms of reversible reactions. Question? Yes. Yes. So we'll encounter some other reversible reactions, mostly in Chem 352, and we will see this principle in action again. Question? Usually it is not in most cases. It could be in some cases, but in most cases, your intermediates are going to be higher in energy. They're usually reactive intermediates, meaning they're higher in energy than both the reactants and the products. And that's going to be the case here because these are cationic intermediates that we're forming. They're higher in energy than our neutral starting material and product. Okay? So there is a variant of this reaction. If we use an alcohol instead of water in this reaction, then we can form an ether instead of an alcohol. Okay? I forgot to write the sulfuric acid. We still have to use sulfuric acid in this reaction. But what happens here is we protonate our alkene, generating our carbocation, getting the more substituted carbocation. But then the alcohol, the methanol in this case, will act as our nucleophile. And then after we deprotonate that, what we'll be left with is an ether. Okay? So this is a second way of making ethers. In chapter 9, we learned the Williamson ether synthesis. This reaction doesn't really have a name, but it's basically an analog of a hydration reaction. You're just using alcohol as opposed to water as the nucleophile. Okay, any questions? And you would get the more substituted ether product, just like we get the more substituted alcohol. All right, so let's talk about the halogenation reaction now. In a halogenation, we take our alkene, we react it with a molecule of a halogen. All right, it is XX. And so we're adding one halogen atom, or a halide, to each carbon of our alkene. Okay? So our products will look like this. Okay? These products are vicinal dihalides. We learned back in chapter 8 what vicinal dihalides are useful for. What kinds of compounds can we make from vicinal dihalides? Yes? Alkynes, exactly. Chapter 11 is about alkynes. So next week, this is going to become very important to us as a method of making alkynes, taking an alkene, forming a vicinal dihalide from it, and then treating that vicinal dihalide with two equivalents of a very strong base to make an alkyne. Okay? This reaction only works with chlorine and bromine. The reaction with, we don't need parentheses there, the reaction with iodine is slow and endothermic. Those carbon-iodine bonds are very weak. The reaction with fluorine is violent and oftentimes causes fires. Fluorine is an exceptionally reactive molecule. It's so reactive that it's hard to put it in a bottle because it eats through most of the materials that it reacts with most materials that are used to make bottles or tubing or reaction vessels. So there's only a handful of labs in the world that actually work with F2, and my lab is not one of them, and no labs at BYU are. So we don't use F2. We will only use chlorine and bromine in this reaction. Okay. This is a very rapid reaction. Bromination is very fast. It's so fast that we're going to show you a real-time bromination reaction. Okay. Now, bromine is smelly. Fortunately, in this class, there's not the people sitting up front that we had in the previous hour. So you might not be able to smell bromine too well, but you'll be glad, if you can, you'll be glad that you're wearing a mask today because the bromine is pretty smelly. And I messed up this a little bit in the last class period in that I added my bromine to the wrong test tube. So what they gave me, what the stockroom gives me for this demonstration is a test tube of cyclohexane, an alkane, and the alkane will not react with our bromine. And the bromine is highly colored, it's purple. And so when we add the bromine to the alkane, there will be no reaction. You can see this test tube is slightly colored because I added the bromine to it by mistake. That was supposed to be the control for this hour. But I'll go ahead and do some more. I'll add some more bromine. So you'll see that when you add bromine to an alkane, the bromine is not consumed. The bromine color, this deep reddish purple color, is retained. Okay? So bromine in an alkane, nothing happens. Now we're going to take an alkene. This is cyclohexene. And we're going to add bromine to cyclohexene. And it's going to react so fast, the color is just going to disappear as it drops in. Okay, I'm dropping it in, and you see no color. It's being consumed as soon as it's hitting the alkene. Let's do some more. Okay, I filled up my pipette with bromine. I'm dripping it in. You can hear some hissing and maybe see some splattering if you're close enough. It is an exothermic reaction, and it is a very fast exothermic reaction. Okay? So one of those rare reactions in organic chemistry that's fast enough we can actually perform it as a demo in class. Okay? All right, so halogenation, very fast. We have our dihalide here that is colorless. It's consumed our colored bromine. We're going to cover these things up so that I'm not smelling them. Okay? And in fact, I'm going to go ahead and put this down below, hopefully not contaminating any sacrament bread that might be left here. Okay. So let's talk about the mechanism of this bromination or halogenation reaction more generally. We're going to give some, the first thing we need to ask ourselves is that we know that our alkene is nucleophilic. Our halogen is nonpolar. There's no dipole here. So how can our halogen act as an electrophile? This bond is not polar. There's no partial charges. What property does chlorine and bromine have that would allow it to be electrophilic? Yes. It is very polarizable. So the electron cloud of bromine or chlorine is loosely held because we're talking about third or fourth row elements. And so as an alkene approaches a molecule such as bromine or chlorine, the electron cloud of the bromine or chlorine will adjust as that electron-rich alkene approaches, and you'll end up with a temporary dipole as the electrons in the bromine-bromine bond will move away from the electrons of the alkene. So the polarizability of the halogen molecule is what allows it to react rapidly with alkenes. Question? So iodine is more polarizable, but the carbon-iodine bond is significantly weaker than the carbon-bromine bond. And so the sigma bonds you're forming are just too weak for that to be a useful process. Okay, very good question. Yes? Yes, iodine size, and so those bonds are longer, and so they're weak. So we're not, they're pretty close to the same, maybe even weaker than a pi bond, if I remember correctly, but they're in the ballpark of a pi bond. They're some of the weakest carbon sigma bonds to carbon that we have in chemistry is the carbon-iodine sigma bond. Yes? Fluorine would be too reactive, yes. Well, the carbon-fluorine bonds are going to be strong, so it's going to be highly exothermic. There are other reasons for fluorines. I'm not enough of an expert on fluorine. I avoid it, and so I can't really explain all the nuances of its high reactivity. But for some reason, it's highly reactive, and it chews through almost anything it encounters. So fluorine is too reactive, iodine is not reactive enough. So chlorine and bromine have the right reactivity for this reaction. Okay? So a little bit of data that we have here. So if we take, so this is the reaction I did for you in the test tube. I had cyclohexene, and I reacted it with bromine. And this reaction gives a dibromide, but the bromines are only going to be trans to each other. Okay? Is this product chiral? Yes, this is chiral. So because our alkene and our bromine are achiral, we have to form a racemic mixture. Okay? So we're going to obtain a 1-to-1 mixture of the enantiomers of this dibromide. But we're only going to get the trans product. Okay? So what kind of addition is this? So the two terms we have are syn and anti. This is anti-addition. So we learn that in a halogenation reaction, we only see anti-addition. Okay? That's a sign that the mechanism's different from hydration and hydrohalogenation because those give us anti and syn addition. Okay, anti-addition only. The second point is that there are no rearrangements. Okay? If there are no rearrangements and we get anti-addition, what intermediate can we conclude is not forming? There's no carbocation. If we had a carbocation, we'd see syn and anti-addition. We would see rearrangements. So we have to draw a mechanism for this reaction that does not involve a carbocation. Okay, so I'm going to draw an alkene, and I'm going to use wedges and dashes to show that my alkene is perpendicular to the chalkboard. Okay, so this alkene is like this, perpendicular to the chalkboard. Okay, we're going to react it with bromine. And as these two reactants get close together, we will have a temporary dipole due to the polarizability of the bromine. So that will allow our nucleophilic pi electrons to attack the electrophilic end of that bromine molecule. And that will cause the bromine-bromine bond to break. So far, this is analogous to what happens when an alkene reacts either with HX or with H3O+. But something else has to be happening. Otherwise, if this is all we were doing, we would end up with a carbocation. And so the something else is enabled by the fact that unlike a proton, our bromine atom contains lone pairs. So while the pi electrons are attacking the bromine and the bromine-bromine bond is breaking, one of the lone pairs on the bromine atom that's getting attacked can come back and form a second carbon-bromine bond to the other carbon of the alkene. Okay? So let's draw the transition state. We're going to have a partial pi bond that's breaking. Let me put in our groups here. We're going to have a partial carbon-bromine sigma bond that's being formed, a partial bromine-bromine sigma bond that's breaking, and then we have a second partial carbon-bromine bond that is forming. Okay, a lot of partial bonds. We've got three curved arrows, three pairs of electrons on the move simultaneously. So this is a little more complicated than some of the steps we've seen in earlier mechanisms. Okay, let's put this in brackets, indicating that it's a transition state. There are going to be some partial charges. We'll put those on in a moment after we draw the intermediate that is formed. Okay, so our intermediate is going to have a three-membered ring with a bromine atom that is known as a bromonium ion, or more generally, a halonium ion. Okay, this term would apply whether it's bromine or chlorine. Okay, it's a halonium ion. The bromine has two bonds and two lone pairs, so that means it has a positive charge on it. Okay, and then we also form bromide. Okay, Br minus. All right. So based on the products of this first step, where do we need to put partial charges in our transition state? Claire? Yep, partial positive on the bromine, it's becoming part of the three-membered ring, and then a partial negative on the bromine that is leaving, essentially. Okay. All right. So this is going to be a reactive intermediate, higher in energy, positively charged intermediate, and so similar to carbocations, it is going to be the slow step. As you saw, it's not that slow, but it is slower than the next step of the reaction. Okay, so this is the rate determining step. Okay, so hopefully our halonium ion reminds us a little bit of an epoxide. Okay, it's going to have ring strain in it like an epoxide. So similar to an epoxide, a strong nucleophile, such as bromide, is going to be able to open that halonium ion to give us our product. Okay, so, and like with an epoxide, that ring opening process is going to be an inversion or a backside attack. Okay, so that's going to give us a product looking like this. Okay, so this mechanism nicely explains the anti-addition because the ring opening of the halonium ion would proceed by a backside attack. And so that explains how we will always be getting anti-addition. And we haven't drawn any carbocations, and so that's consistent with the fact that we don't have any rearrangements. You might be wondering, though, the fact that we formed this halonium ion proves that it must be lower in energy than a carbocation, right? If we weren't using this pair of electrons here, we'd end up with a carbocation. But we know we're using that pair of electrons because we only get anti-addition and there are no rearrangements. So that's very strong evidence for this pathway as opposed to a carbocation. But then the question becomes, why? Why is this strained halonium ion more stable or lower in energy than an unstrained carbocation? Any ideas? Okay. Yes, Claire. Okay, it can, and there's a reason for that. Any ideas as to what that reason is? Yes. Bromine is bigger. Yep. We've got there's another feature of bromine. Yes. You should be more confident. That's exactly right. So bromine, a positively charged bromine, still has the octet, or can still have the octet. And in this case, it does. We have 8 electrons around this positively charged bromine. A carbocation cannot have the octet. A carbocation only has 6 electrons. Okay? And so even though there's ring strain here that you would not have in a carbocation, the fact that a bridged halonium ion has all of its atoms with satisfied octets makes it more stable than the corresponding carbocation, where the positively charged carbon would not have the octet. Okay? So that is why a bridged halonium ion is more stable than a carbocation. Okay? Any questions? Yeah, another question. Okay, in this case, if all 4 of these groups were the same, there would be no difference. But if they're different, then there would be a difference. Okay, so I haven't drawn R groups or hydrogens or anything like that. But if this was just ethylene, for example, you wouldn't have a difference at all. Okay, but if it was not ethylene, then you'd start to see differences. Okay, and in that regard, let's go ahead and draw on the board here. Let's see what would happen if we had cyclohexene. We react that with chlorine. So we're going to make okay, here's our bridged halonium. Here's our chloride ion. Is there going to be any difference whether the chloride attacks the carbon on the left versus the carbon on the right? No difference. It's going to be the same. In both cases, it would attack from the bottom. It's going to attack opposite from where the chlorine of the chloronium ion is. But you're going to attack with equal rates to the carbon on the left and the carbon on the right. Okay, so that's going to give us this compound. This is the product from the chlorine attacking on the left and this compound. This is the product from the chlorine attacking on the right. What's the relationship of these two compounds? They're enantiomers. They're non-superimposable mirror images. So we get a one-to-one mixture of a racemic product. But those groups are both trans. They're not going to be cis to each other. So we see something interesting if we look at the reaction of bromine with diastereomers. These alkenes are cis and trans isomers, or E and Z isomers. Okay, so we have cis-2-butene, which is also Z-2-butene. Either name is fine. We react that with bromine. We obtain these two vicinal dibromides, and these are enantiomers of each other. These are non-superimposable mirror images. We take the trans or the E isomer. We react that with bromine. We get a product that is a diastereomer of the product up above, and in this case, it is achiral. It is a meso compound. How can we tell that it's a meso compound? There are two ways to do so. One is if we rotate 180 degrees about this carbon-carbon sigma bond, now our bromines are going to be eclipsing each other, and what we find is that this hydrogen will come forward and mirror that hydrogen. The methyl group will end up back and mirror that methyl group. So we'll have a plane of symmetry, and we'll be able to see that plane of symmetry if we do a 180-degree rotation. The other way we can tell that this molecule is achiral is if we take either one. Let's just say we're going to take the one that's drawn on the right. If we just flip that over and superimpose it on the one on the left, we find that it superimposes perfectly. So it is a superimposable mirror image, meaning that the two structures are identical. Okay? So the halogenation reaction is what we call stereospecific. Okay? So a stereospecific reaction is a reaction where each of two diastereomers of the starting material, SM is an abbreviation that I like to use for starting material. So each isomer provides, each stereoisomer of the starting material provides a specific stereoisomer of the product. So we see that there's two diastereomers of our product, our chiral dibromide and our achiral or mesodibromide. And we see that the cis-2-butene is always going to give us the chiral dibromide as a racemic mixture. And the trans-2-butene is always going to give us the achiral or the meso dibromide. So that means it's stereospecific. This is a subset of stereoselective, which was a term that we learned earlier. We learned that back in chapter 8. Okay? Any questions about the halogenation reaction? Yes, please. Yes, but that depends exclusively on which isomer of the starting material you have. So that tells us that the cis is always going to give us the chiral, the trans is always going to give us the achiral. Okay, so that's there's going to be no crossover there. That's what stereospecific means. Okay, so there's a reaction that's closely related to the halogenation reaction, and that is known as halohydrin formation. We take an alkene, we're reacting our alkene with a halogen, and again it's going to be bromine or chlorine, but this time we're performing the reaction in the presence of water. And instead of adding 2 halides, 1 to each carbon, we're going to add an OH to 1 carbon and a halide to another carbon. So this product is referred to as a vicinal halohydrin. Vicinal meaning adjacent carbons, halohydrin telling us that we have a halogen and an OH group. Okay. So this reaction is similar in mechanism to the halogenation. So we're going to look at it on the screen and just point out the differences. Step 1 is going to be the same. Our alkene is going to react with our halogen molecule, chlorine or bromine, in the slow step to generate a bridged halonium ion as well as a halide ion. Okay. Step 2 is going to be different. Instead of the halide acting as a nucleophile, we're going to use water as a nucleophile. We'll talk about why in a moment, but because the water is a neutral nucleophile, we end up with a positively charged species that we then have to deprotonate with a second equivalent of water to form our product. So you see we're generating H3O plus here, which is just going to form a salt with our halide. Okay? So similar, we have the same bridged halonium ion intermediate, but why on earth is a weak nucleophile, water, reacting with this intermediate in preference to a strong nucleophile, halide? Okay? Okay? Yes, yes, you're correct. So we don't use water if possible in the halogenation reaction. But in the halohydrin reaction, we're using water as a co-solvent. We're using large quantities of water. So what we end up with is just a handful of bromide ions swimming in a sea of water molecules. And even though those bromide ions are stronger nucleophiles, the concentration of the water molecules is so much higher that the water molecules are going to collide with the halonium ion much more frequently than the halide will. So we use an excess of the water, a huge excess of the water, to allow the weak nucleophile to outcompete the stronger nucleophile. Okay? Question, Claire? Yes, yes. Chlorine and bromine only. Okay? All right. There is a slight addendum to the answer to your question, which is that there is an alternative reagent that you can use instead of bromine, and that's called NBS, or N-bromosuccinimide. And I'll draw that for you here. NBS looks like this. And this nitrogen-bromine bond is a weak bond, and this molecule can decompose, and it's going to slowly release bromine. Okay? Now, bromine, you guys were sitting far enough away probably to not smell it, but I got a double whiff of the bromine because I did the demonstration twice. It's not very pleasant. Bromine is a stinky molecule. NBS is an essentially odorless solid, much more convenient to work with. So in the lab, most people would use the NBS as opposed to the Br2 for this reaction. On paper, you can write either one. But if you use NBS, you have to use aqueous DMSO as the solvent, okay, in order to get everything to dissolve. To get this to dissolve well, you have to have DMSO mixed with your water. And so it's important, if you're going to use this as a reagent, to specify that you're using aqueous DMSO. Okay? All right, let's talk about stereochemistry for a moment. Because of the similarities in mechanism, we're going to have an anti-addition only in the halohydrin formation, just like we do in the halogenation. Okay. So the OH and the halogen are going to be trans to each other. Is this chiral? Yep, so we will form its enantiomer. Just to save time, I'm just going to write plus enantiomer, but you'd want to draw them both out, usually on an exam. Okay. There's a bit of a difference in terms of the stereochemistry between halogenation and halohydrin formation. And that comes when we look at the reaction with trans 2-butene with bromine and water. If we back up a couple slides, we saw that when trans 2-butene reacted with bromine itself without water, we obtained an achiral meso compound. Over here, we see that when trans 2-butene reacts with bromine and water, we get a chiral product. We get enantiomers. Why? What's the difference? Yes, please, Claire. Yes. So in the halogenation, we're adding two of the same atom to our alkene, and that's what allows us to have a plane of symmetry in the molecule. In this case, because we're adding two different groups, a bromine and an OH, there's no symmetry, and therefore both products from cis-2-butene and trans-2-butene, both products are chiral when you're performing a halohydrin reaction. They're going to be diastereomers of each other, but they're both going to be chiral diastereomers as opposed to one being chiral and one being a meso compound. Okay, so no symmetry possible in this product, so it is chiral. Any questions? So there's another question that we need to answer. If we have an unsymmetrical alkene, meaning a more substituted and a less substituted carbon of our alkene, and we react that with bromine and water, which group will attach to which carbon? Meaning, are we going to get the more substituted alcohol, or are we going to get the more substituted alkyl halide? Which of these products is going to form? We're going to explore that question in the context of an iClicker question. So let's get our iClickers out. Go ahead and talk to your neighbors. A couple things I'll say about this as you're getting ready. This plus minus notation, that just means that these are all racemic compounds. We've only drawn one of the two enantiomers, but plus minus means this plus its enantiomer will form in each case. There's only one product that forms in this reaction, one of these four. Okay. We've already talked about the stereochemistry of this process. It's the same as the halogenation. So what we're trying to figure out is, do we get the more substituted alcohol or the less substituted alcohol? And I'll give you a hint as you're thinking about this. Think of your bridged halonium ion as an epoxide. Think of the two methods we have of ring opening of epoxides, and think of which of those two methods the bridged halonium ion more closely resembles. And that will help you come up with the answer to this question. So go ahead and chat and answer. Okay, and I've drawn a diagram on the board that might also help you in this discussion. I've drawn the two possible transition states for this reaction. Okay, so you can take a look at that and hopefully come up with an answer in the next minute or two. Okay, let's try to come up with our final answer in the next 30 seconds or so, maybe. Okay. About 10 more seconds. Let's get our final votes in here. Any more votes? Once I press stop, any ballots postmarked after that time will not be accepted. They will not be counted. Okay. All right, we're stopping. Okay, so first of all, in terms of stereochemistry, which are the two products that come from anti-addition? Okay, B and D. So we can eliminate A and C because those are from syn addition. So do we get the more substituted alcohol or the less substituted alcohol? We get the more substituted alcohol, and most of you came to that conclusion, so that's good. Why? Who would like to briefly explain why before we adjourn? Yes? Exactly. So of the two possible transition states, you want the one with the partial positive charge on the more substituted carbon, meaning that the water is going to attack the more substituted carbon. So which of the two methods of epoxide ring opening does this resemble? The ones with strong nucleophiles or the ones with HX? The ones with HX, where we protonate the oxygen, we have a positive charge on the oxygen, and the carbon-oxygen bond breaking is more advanced than the bond formation. The same thing happens here. This is an SN1.5 process, where at the transition state, the carbon-bromine bond breaking is more advanced than the carbon-oxygen bond formation process. And so because of that, the water will attack the more substituted carbon. Very similar to epoxides being opened by HX. Okay, we'll stop there. Have a good weekend. Make sure you're ready for the quiz on Monday.